Hi, welcome back. So we have already derived how many atoms a single pKa can displace. And that was on the order of 256 to 500 atoms. Now we want to ask how many pKa's a neutron can make. Because, so let's look at the picture, right? So this neutron, this little black dot that I'm going to draw here, and it hits a pKa, which is typically an iron atom we're talking about. And that atom, depending on the energy, let's say for energy of 35,000 electron volts or 35 keV, the number of pKa's will be somewhere on the order of 256 to 500 displacements. So yeah, 256 to about 500 displacements are made per pKa. Alright. So this neutron, once it hits this pK, it will bounce off with slightly less kinetic energy. So because all the kinetic energy has come here, but we've got to remember the incoming neutron is about 1 MeV. If you're talking about 1 MeV neutron, that's how much energy this pK will have. So this one will have equivalently, I think about 965 keV. That's still a lot of energy, and it's probably going to hit another nucleus, and then it's going to make that atom, the nucleus of the atom, it's going to make it a pKa. So how many can this neutron displace on average? And of course, as the neutron flies through the nucleus, this complicates the picture, right? As the neutron flies through the nucleus, flies through the lattice of atoms, it can either hit or miss the atom. Because you see, most of the atom is actually the electron cloud, which the neutron does not interact with. The only part the neutron really can interact with in a collision is this nucleus. And sometimes the neutron misses the nucleus, sometimes it hits the nucleus. So how can we factor this probability into account? Now, first, I want to introduce the concept of cross-section to you. So this is what this cross-section here is talking about. So let's say, for example, we have a certain flux of neutrons. So in a nuclear reactor, we don't only have one neutron, we have several. And we are not going to, account for each of them. We're not going to do math for each of them, so to speak. But we can consider this as some kind of a group, and we call the flux phi, which is the number of neutrons going through a unit area per second. So flux is usually measured in number of neutrons per unit area per second. So let's say all this neutron flux is going through a metallic lattice or an atomic lattice. Atomic lattice. It could be a metallic lattice or even a ionic lattice, as is in the case of nuclear fuel. Now, what affects the rate at which the neutrons actually scatter off, or actually hit the lattice and bounce off? So when it hits the lattice and bounces off, this is known as a scattering reaction, or scattering interaction. It may not necessarily be a nuclear reaction in that sense. So what affects the rate at which these neutrons actually hit a single of this lattice? And there are several factors that affect this. Firstly, we may talk about the density of the atoms, the atomic density. So we have factors affecting the chance of hit. The factors affecting the probability of hitting. So firstly is atomic density. And the other things we want to consider, the thickness of the lattice. Because let's say you have a lattice 3 atoms thick. Well, it's quite likely that most of the neutrons are going to go through. But if you have a lattice that's about 30,000 atoms thick, or several millions or billions of atoms, if you have a few cm thick of steel, for example, the likelihood of the neutron in this neutron beam actually hitting a single nucleus is going to increase. So the thickness of this lattice will indeed affect the probability of the neutrons hitting one of these atoms, or the nucleus of the atom. And thirdly, we want to consider the neutron flux. So the probability of the scattering event occurring, it also depends on the flux. Now this one's quite intuitive. The more neutrons you have hitting this lattice, the higher the probability of this scattering interaction taking place. Because more neutrons means more knock-ons. Anyway, so how do we factor all these in? So we can write it as such. Let's say we have R, or we have this reaction rate, or we can also call it the interaction rate in interactions or reactions per area, and that is equals to the atomic density, which is the number of atoms per cm cube per volume. So we multiply that by the thickness, as discussed before. Thickness, let's say in length, and we multiply that by the neutron flux in neutrons per cm squared per second, or neutrons per area per second, times a constant of proportionality. We just call it that sigma. And sigma is, if you consider all these units, it'll be in units of area. So let's make it more consistent. So the atomic density, let's just call it Na, or row of atoms. So we have number of atoms over a cm cube, for example. The thickness, we can just call that T in cm. The neutron flux, which I call that phi. And I'll put that in neutrons per cm squared per second, times the constant of proportionality, sigma. Put it in cm squared. Now this constant of proportionality, we call that the cross section. So the larger the cross section, or the larger the area, the more the probability of the interaction between the flux and the lattice. That's what we call the cross section. Okay, now let's move on. So the other unit I want to introduce you when we talk about cross section, so we go cross section. Sometimes we use the unit of excuse me, cm squared, but often you will see cross sections online, especially from the sites known as the National Nuclear Data Center, or nndc. They will come in the unit of barn. So let me take out the equal sign first. They will come in the unit of barn. So how much is a barn? So just if you want to talk about conversions, okay, let me get more space. Okay, Yeah, you want to talk about more. You want to talk about bunt, one bunt. So one barn equals 10 to the minus 24 centimeter squared. So one barn equals to 10 to the minus 24 centimeter squared, or 10 to the minus 28 meter squared. So you can imagine that's a really small unit of measurement for area. 10 to the minus 28 meter squared. Okay, so now let's try and plug some numbers into this equation. All right. Okay, so yeah, we've introduced the concept of cross section so far, and in this video, we want to also assume that the neutron flux is constant. So if you want to start plugging numbers, we just make some simplifying assumptions. We assume that the neutron flux is constant as it passes through this lattice, and that assumes that the number of neutrons that are consumed in the interaction or reaction is negligible, which is in this case quite true for scattering. So we are assuming that this equation holds when the neutron is not absorbed. So the assumption is that no neutrons absorbed. Is this even straight? Sorry, try to make it straight. Yeah, the assumption is that no neutrons are absorbed. And number two, no significant slowdown. Now, of course, is that true? For this case, you can see that 1 MeV, which is 1000 kilo electron volts, and 965 kilo electron volts is a pretty similar kind of a number. So you can assume that the slowdown is like what, 3%. So the slowdown may not be significant for our case. Otherwise, we will actually have the neutron flux decreasing as some function of thickness. Yeah, especially if absorption is being considered. So we'll just make this simple. Now, for this equation, let me write it. R equals to, maybe we have this rho to represent atomic density, times phi times T times cross-section sigma. So if we look at this reaction rate, we have interactions per area. But if we want, we can simplify it into like interactions per volume. So this is interactions per area or reactions per area. Yeah, sometimes you will see equations in this form. R equals rho phi times sigma. So what happens to the thickness? Well, this R is in interaction per volume. So this thickness you'll just divide both sides by T, so R by T, and that will give you this R over here. So we can call this R prime, but sometimes textbooks won't help you to differentiate, or in your course or study you might not differentiate, but just know that there's this fundamental difference. Sometimes it can be slightly confusing, but yeah, hope this clarifies things. So now, after all that deriving and explaining what a cross-section is, let's try and plug in some numbers to find out how many displacements per atom, which is a neutron damage or radiation damage, we are actually sustaining in our material. So in a nuclear reactor, our typical flux will be somewhere on the order of 3.11 times 10 to the 13 neutrons per cm squared per second. and that is I've taken that value from nuclearpower.net. And how do we then calculate this atomic density of iron? So we find that the density is in somewhere on the order of 7.874 grams per cm cube. This is the mass density. The molecular weight is about 56 atomic mass units, or 56U, and the Avogadro constant is 6.022 times 10 to the power 23. Sometimes you use E, especially in Excel. So this is atoms per gram mole. So 56 AMU, or 56 grams per gram mole. It's the same thing. Okay, so with that we can calculate our atomic density. So we just put a subscript atom to differentiate between this and density. We've also, sometimes we can use the letter rho. So how many atoms do we have per centimeter cube? So we'll take the mass, 7.874 grams per cm cube, times, okay, we'll try and convert this to the number of moles. So we will have 1 over 56 gram per gram mole. So we have, in effect, we are converting it to moles per cm cube. So now that we have a moles per cm cube kind of unit, we just need to times Avogadro's constant. So we have number of moles per cm cube times this, Avogadro's constant, and then we can get the atomic density. So let me go and type all this down in Excel. 6.022 E23, 1 over 56, 7.874. Okay, I'm going to use a product function. Okay, you probably can't see what I'm doing, but never mind. Alright, so we'll get the answer at about 0.46736 times 10 to 22 atom per cm cube, which is pretty reasonable. That's the order of magnitude you should expect. Okay. Now, what about this? What is this reaction rate? Well, we've already considered the atomic density. We've also considered the flux. So we are using this interactions per volume kind of a term, or reaction per volume. So now all we need to do is find the cross-section. Now I can show you in another video how to extract this cross-section data from nndc, which is the National Nuclear Data Center. Okay, I'll show you in the other view, but for now just take it from me that sigma is about 2 to 3 barns. So we'll just take about 3 barns, because the graph is pretty hard to read, so we just estimate. Now let's multiply them together. So you just have to multiply. R equals to 3 times 10 to the minus 24 cm squared. So that's the cross section. I'll multiply by the neutron flux. So that's neutrons per cm squared per second. That's going to be multiplied into the atomic density of iron. So that is on this order of magnitude. So that can give you the reaction rate or interaction rate per volume. So reaction rate, I'm just going to call it reaction rate, right? So let's do some quick Excel. 3.11 10 to the 13, 3e minus 24. Let's take the product. Okay. 7.9 times 10 to the 12 interactions per centimeter cube. So in 1 cm cube of the steel with this much flux in this cross section, it's bound to happen about this many times. So there's interactions per cm cube per second. Yeah, I should put that here as well. Per area per second, per volume per second. So these are in rate units. So that's the interaction rate per area and volume respectively. So we multiply them together and we get some reaction rate. And how long is this nuclear reactor supposed to last? And how much radiation damage will it sustain? So in a typical reactor, we can get we kind of want it to last about 30 years. So maybe every 3 to 5 years you have some kind of repair. So we want to calculate how many so-called pKa's are generated in that little cm cube per unit volume during that kind of time span. So we have about 3 to 5 years. Okay, so let's just take 5 years to kind of help us run some numbers by. Okay. Excuse me. So 5 years, right? And that's equals to 86400 seconds per day times 365.25 days per year times 5 years. So that's just converting it to the number of seconds that we have radiation damage hitting the thing. So let's convert it. 86400 365.25. That accounts leap years as well. So we take the product of all of this and we arrive at a very large number of seconds. 15778,000. Okay, my commas are all in the wrong place. Alright, I hope you don't mind. Okay, let me try and put it in the right places. 15788,000 seconds. That's a lot of seconds. Okay. And then the next question we want to ask we're going to continue answering our question. How many interactions, how many scattering events do we have in this whole 5-year time span? So R equals to 7.9 times 10 to the 12 times 15778,000, and we'll just multiply that in the calculator or Excel, which is a great calculator. So we'll have 1.24653 times 10 to the 21 scatter per cm cube. So this is the reaction we're talking about. And if you want to talk about per atom basis, well, yeah, you can just divide that by this atomic density. If you want to talk about per atom basis, okay, so that will give you an idea. So 8.4376 times 10 to the 22. Wait, not 8.4376, 8.46736 times 10 to the 22. So you want to talk about per atom basis. Okay, That will give you scattering events per atom, or equivalently pKa's per atom. Okay, let's just run that through the calculator. This is about 21 over this much. Okay, 0.01472. Okay, that's how many pKa's you're getting on average. So that's the number of times the neutron is colliding per atom during this 5-year period. So how many displacements per unit or displacements per atom is that? Well, we have calculated previously. We have about 256 on the conservative side, 256 displacements, right? Displacement per pKa, and we have this much pKa's per atom being made. Let's just take the product of these two numbers. So dPa, if you are using these assumptions, 0.01472, and that multiplies into 256. All right. Okay, so we will have about 3.6873 dPa, about 3.7 dPa. So that's what do you call it? Yeah, that's a lot of dPa's, displacements per atom. That means on average, each atom is being knocked from its position 3.7 times. So why isn't the material destroyed in this case? For one, let's say you have this lattice. Before the neutron messes it up, and after the neutron messes it up, we will have some vacancy and interstitial pair, which is this Frankel pair here. Well, why doesn't this material just get destroyed? So sometimes the vacancy and interstitial can recombine and release heat, and in that sense the damage is negated. So that's what happens for many of these vacancy and interstitial pairs or Frankel pairs. Furthermore, we may be overestimating the number of displacements because we assume these atoms are large spheres. But in reality, they are a soft electronic cloud surrounding a hard nucleus. Sometimes if the pKa is really fast, all it does is just to ionize some electrons of this atom, and it will not cause the atom to be displaced from its location. So this is another kind of another factor we have yet to consider in our calculations. So this phenomenon is known as electronic stopping. So this pKa or some other ion is traveling through this lattice and is ionizing atoms along the way, and thereby it loses energy. This is known as electronic stopping. Electronic stopping. And we want to see how big an impact they play with our collision cascade. So that's for next future videos. Thanks for watching. I'll see you guys next time. Bye bye.